Recording. Okay, so hello everyone. Welcome to Deep Learning Theory and Data Science. Today we're going to continue our discussion about the DeepNet spectra and the boomlet of studies of DeepNet spectra. So in the previous lecture, I've shown you a collage of all the different measurements that people have made in the literature, primarily in the last couple of years. And all of these experiments are showing different eigenvalues of different quantities in deep learning. In the seventh homework, you'll actually implement an experiment that will calculate the eigenvalues of the Hessian of a deep network. Some have already implemented it with great success. So I remind you, in the previous lecture, we've discussed how in the 90s, Jan LeCun created an interesting measurement where he looked at the histogram of the eigenvalues of the Hessian at convergence, or after many iterations of gradient descent. And here you can see the eigenvalue magnitude versus the number of eigenvalues in each bin. And we mentioned that there is a set of eigenvalues which are large, and we call them outliers. And there's a majority of eigenvalues which are rather small, and these are called the bulk. And since the 90s, other researchers started looking at the eigenvalues of the Hessian, for example, Dauphin, who again looked at the spectrum of the Hessian, and Levon Sagun in 2017, who here you can see the experiment he made. Now, in 2018, there was this work that I wrote that showed how you can actually calculate, or estimate rather, the spectrum of the Hessian for very large networks, for example, VGG11, which has tens of millions of parameters. And again, in those experiments, you can see how the majority of the eigenvalues are rather small and concentrated around 0. And there is a small set of eigenvalues which are larger. So at this point, let me ask you a question. Can you identify a strange phenomenon in the plot I'm showing you? Is there something that jumps to your eye that seems rather strange, bizarre?
The number of outliers are the same as the number of classes?
That is one observation. That is correct, Tristan. That is one observation that is interesting. The number of classes in all of these data sets, MNIST, Fashion MNIST, and CIFAR10, is equal to 10. And the number of outliers is also equal to 10. Is there something else that's kind of strange about these plots? The bulk has the same shape. Maybe the same shape. There's something else maybe that's strange about this.
I think it's the bulk that spikes. They all spike around 0.
There's spikes in the bulk around 0. Yeah, there's some things here, but something else about the bulk. So if you are doing a convex optimization and you calculate the Hessian at convergence, what do you expect the Hessian to satisfy?
You'd expect it to be positive semi-definite, at least.
Exactly, positive semi-definite, right? Because the definition of a critical point, right, a local minima, would be that all the eigenvalues are greater or equal than 0. However, we can see here that in many of these experiments, there's a bunch of negative eigenvalues, right? So what does this mean? in human words, what does this mean? We are at a saddle point. That is what it seems to me. Yes. You can see how approximately half of the eigenvalues are positive, approximately half are negative. So it seems like we're stuck on a saddle point. Now, this is somehow surprising because when you are training, in these specific experiments, I was training a network for 300 epochs, and I was really putting my heart into the hyperparameter optimization. So it's not like a silly experiment that was just run in a sloppy manner. Much effort was put into the optimization, but still, the thing that I've achieved is a saddle point. Okay, and then we mentioned in the previous lecture that we can decompose the Hessian into two quantities. So the Hessian is the second derivative of the loss with respect to the parameters of the model. So the Hessian would be something like the second derivative of the loss with respect to the parameters of the model. And you can decompose the Hessian into a matrix called E and into a matrix called G. G is the Fisher information matrix. And in the previous lecture, I've shown you how do you calculate this decomposition. It's just by essentially writing the gradient is equal to the derivative of the loss with respect to the logits times the derivative of the logits with respect to theta. And then if you look at the derivative of the gradient, it's a gradient prime, then you need to derive the multiplication. Do you remember such thing? And then once you derive the multiplication, you get 1 times this thing and 1 times this thing. At this point, it's unclear what is the significance of this decomposition, but it might become clear later. And I can just tell you at this point that the Fisher information matrix satisfies one property which is possibly quite useful. Does anyone identify can anyone identify an interesting phenomenon that the Fisher information matrix satisfies? It's not very easy to see from the equation, but maybe some people here are seeing something. So let's say we're looking at an MSC loss, right? In the case of an MSC loss, what is the second derivative of the loss with respect to Z, the logits? In the case of an MSC loss, the second derivative of the loss with respect to the logits would be, oh, someone said it is positive definite. Yes, that is correct. But let me just explain why. Because if you have an MSC loss, this thing is going to be an identity because it's the second derivative of MSC. And then you have the derivative of f with respect to theta transpose times derivative of f with respect to theta. So whatever, call this J. So this whole thing is basically J transpose J, right? And so this is positive semi-definite. So the property that the Fisher information matrix satisfies is that it is positive semi-definite, unlike the Hessian, which can be not positive semi-definite. And in fact, it is not positive semi-definite in the experiments that I just showed you. So since then, since the works that, or maybe in parallel to the works that were studying the Hessian, there were works that were looking at other quantities. So this paper by Li et al. Did the following. Imagine you construct a Hessian matrix. How does the Hessian matrix look like? Let me draw you an example of a Hessian matrix that appears in your homework. Imagine that you have a two-layer network with two fully connected layers, okay? So what are the parameters of the model? They are W1, B1, W2, B2, right? Then the set of parameters, theta, is just the vectorization, it's just a long concatenation of all the vectorized quantities. So it's vec1, I guess you don't need to vec B1, and then vec W2, and then B2. Make sense? Now, notice that the Hessian is going to have a partition that's very intuitive and natural. And the partition is going to be, first you're going to have, let's say, a block. Let's say the first indices correspond to vec W1. The next indices correspond to vec B1. Then you have vec W2 and vec B2, which I have no space for. So you have essentially a block structure to the Hessian where the blocks are defined by this, how should I put this, how would you call this? This partition induced by the parameters. So like the first block, the block, let's color it in red, this quantity in red would be the second derivative of the loss with respect to vec W1, right? Whereas the quantity in, I guess, green would be the second derivative of the loss with respect to first vec W1 and then vec B1, right? Now, in this paper by Li et al., they are looking at the spectrum of the Hessian. H stands for Hessian, G stands for Fisher information, okay? And they're looking at different subsets of the Hessian. Like you can look at the whole Hessian, or you can just pick a certain block from the Hessian and calculate the spectrum for that. Make sense? So it's like looking at the spectrum of a small block extracted from the Hessian. And what you can see, if you look carefully, is 3 curves. Each curve corresponds to a different iteration. So the orange one is at iteration 1, and the purple one is at the last iteration. Now, if you take your magnifying glass and you look carefully at these plots, you can see several things. First of all, as a sanity check, notice that the plots that correspond to the G, which is the Fisher information matrix, are all showing positive eigenvalues, right? There is no negative eigenvalues. So this is expected. The Hessian again shows negative eigenvalues. So this is the Hessian. So this shows that I can in fact code properly, and I'm not the only person who noticed that the spectrum has negative eigenvalues, right? It's always good to see that someone else saw a phenomenon that you saw. Another thing that you can see here is that notice if you zoom in, which actually I can zoom in, do you see how there's an interesting structure that emerges in these plots? What is the interesting structure? Notice how there's a set of eigenvalues here. So this is the eigenvalue magnitude, eigenval magnitude. And on the x-axis, you have the index of the eigenvalue, so index. So this quantity, this quantity right here would be the first eigenvalue. This would be the second eigenvalue, and so on. Notice how there's a set of eigenvalues here which are larger than the rest of the eigenvalues. And then notice how there's a second set of eigenvalues which seems to be shaped in a certain manner, and then you have the rest of the eigenvalues. Do you see the structure? So let me highlight this across the different plots. So there is a set of outlier eigenvalues, then there's more outliers, and then there's a bulk. And this seems to happen in many of the layers. So other people have looked at eigenvalues of other quantities. So in this paper by Verma, they were proposing a method which is called manifold mixup. It doesn't matter what mixup is, but you can think of it as some knob that you can turn on or off to change something about the training. Now, what's more important is in these plots, they're showing you the singular value index versus the singular value, right? So in statistics, this would be called a scree plot. Scree plot is when on the x-axis you have the index of the eigenvalue, on the y-axis you have the value of the eigenvalue, right? This should be compared with a histogram, where in the case of a histogram, here you have a value, and here you have a count, right? So usually a scree plot looks something like this, whereas a histogram looks something like this. I guess it's usually like bars. In any case, what you can see is that they're showing the singular values of the representations. What are the representations? It's basically the features in the network at some layer, right? And in this case, it's layer 1. In this case, it is layer 3. And what you can see is different curves of singular values, and notice how they're saying that these plots are only considering the representations of a particular class. That is also important, a particular class. So essentially you take a network, you extract the features at layer, let's say 1 or 3, and then you pick all the features which correspond to the cats. And then you calculate the singular values of those features and you get this thing. Can anyone identify here an interesting phenomenon that happens? Does something pop to your eyes? Something interesting about this experiment?
Yeah, it's almost like it's approaching a rank 1 matrix,
Yes.
which would be like neural collapse, I guess.
Exactly, yes. So Tristan with the eagle eye. Do people say eagle eye in English? I think that's, oh, okay, cool. So Tristan with the eagle eye, notice that this matrix is almost approaching rank 1. That is correct. So basically there is a eigenvalue outlier and a bulk. So Amireza is asking, number of zero eigenvalues of feature information matrix increases as function of iteration. Number of zero eigenvalues increases as function of iteration, which can be interpreted as null space of feature matrix is increasing as time goes on. Is there any known reason for this? I don't think there is a known reason, but maybe as we continue discussing this topic, you might find the reason. At this point, it's hard to explain what's the reason, but maybe in a lecture or two, you would see what's the reason. Okay, and yet other researchers looked at the eigenvalues of different quantities. So this is Martin and Mahoney from Berkeley. They were interested in the singular values of the weight matrices in the network. And so in this case, for example, they looked at the mini AlexNet architecture. They looked at the fully connected layer, and they calculated the singular values of the weight matrix, which are basically the eigenvalues of the weight matrix transpose times itself. And what you can observe is, again, there is a certain bulk, a big number of eigenvalues which are concentrated together, and there is a set of eigenvalues which are emerging. Okay. In this case, you can see that they averaged over 10 runs, the spectrum. So that seems to indicate that the number of outliers is probably 10 times more than what it should be. And in their work, they looked at the singular values of many weight matrices in computer vision networks and also natural language processing networks. And they showed that they were actually not interested in the structure of bulk and outliers. What they were more interested is in the shape of this, let's say, empirical distribution. And so the set of questions that arises from this is, first of all, what is causing these outliers to appear in all of these different experiments? How many outliers are there? Tristan observed that there is a number of classes outliers. But sometimes we saw that there's more outliers, like in the Fisher information, you could see that there's outliers and there's a few more outliers and only then you have the bulk. And another question is, are these outliers significant in any shape or form? Maybe they're just some artifact of an experiment. Maybe they're insignificant, meaningless, waste of time to consider. And if they are significant, why are they appearing in every single measurement we're making? That's another question you might ask yourself. And Tristan said the words neural collapse, right? So it seems like something in the features is happening where the features are tending to a low rank structure, and it seems to indicate that there is some relation to neural collapse as well. So in order to answer these questions, I would like to first do a very short review of random matrix theory. So if you want to learn, random matrix theory in depth, you should take a course in random matrix theory. But what this is meant to do is just show you some of the biggest highlights of random matrix theory. And I think this is important because it would give you some intuition about what are some possible mathematical explanations for why some of these phenomena are occurring. Okay. So here we go. So imagine that we take a matrix which we call Z. And the matrix has entries, each of which is distributed as a normal distribution. Each entry is a one-dimensional normal distribution with mean 0 and variance 1 over n. N is the number of rows or the number of columns in this matrix. Now, notice that we can take this matrix Z and we can calculate its n eigenvalues. Now, because the matrix is because the matrix is, we can take these eigenvalues and we can actually plot them. So here you can see a plot of the different eigenvalues, and each black dot is a different eigenvalue, right? So why are the eigenvalues plotted in a two-dimensional plane? Why are they plotted in a two-dimensional plane? Because the matrix Z is not symmetric. If the matrix Z is not symmetric, we have complex eigenvalues, right? Now, what can you see immediately from this plot? You can see that the eigenvalues seem to be confined almost to a circle, And so one can actually prove that if you take n to go to infinity, then the eigenvalues are going to be distributed uniformly over the unit circle in the complex plane. So here you can see a blue circle, the unit circle, and the uniform distribution is basically just pick a random point with equal probability in this circle, right? Now, this is one type of random matrices people like. Another type, oh, I should mention that this is called the circle law because you get a circle. Another type of random matrices people like are random matrices where Z is again chosen the same way. So it's normal Gaussian zero mean unit variance. But instead of doing the eigenvalue decomposition on Z, we're doing the eigenvalue decomposition on a symmetrized version of the matrix, where you do Z plus Z transpose over 2. How many RMT experts are sitting in the crowd and I'm wasting their time? Is there many RMT experts? No? Oh, I'm not wasting your time. Okay, that's good. So this matrix is a symmetrized matrix because it is symmetric, right? It is symmetric. Now, because the matrix is symmetric, we can do... Is there a good book on this you would recommend? I can give you a list of books I would recommend. I wouldn't recommend a single book. But it depends. Maybe you could discuss it at the end of the lecture and tell me what are your needs, if that makes sense. It depends, like, what do you want to do with this? So because this matrix is symmetric, then the eigenvalues now are real, right? And we can do an eigen decomposition where we have U lambda U transpose, where lambda is a diagonal matrix with the eigen values, right? Now, a natural experiment to run would be to take all of these eigenvalues, lambda I from 1 to n, and to compute a histogram of these eigenvalues. Very natural, right? Do you like histograms? They're very useful. So here you can see at the bottom a histogram. So it says simulation of this, so it's called the semicircle law, using 1,000 samples of the eigenvalues of a 1,000 by 1,000 matrix. So basically you take a 1,000 by 1,000 matrix, calculate the eigenvalues of the symmetrized matrix, and you just create a histogram, and you observe this most beautiful shape you've ever seen in your life of a semicircle, it's called, half a circle. And you know, mathematicians have spent a lot of time, energy, and mental capacity to prove that the eigenvalues of such matrices Z after symmetrization tend to a distribution which is called the semicircle law. And here you can see the probability density function, right? So this probability density function says, you know, what's the probability? Basically, using this, you can calculate what's the probability of finding eigenvalues in each one of these beans, right? Okay. So one can, so this was the semicircle law. Now we move to n, the radius depends on n. No, so n, I should emphasize, n tends to infinity. N tends to infinity. In order to get a mathematical law, your eigenvalues need to tend to infinity. And so the histogram, when it tends to infinity, it becomes a probability density function. I feel like it's almost sacrimonious to say this sentence in mathematics. A histogram tends to a probability density function, but it's okay. So did I answer the question, Jack? Okay. So another set of, there is another distribution that people care about, and I would say this is the one that people care about the most, where you take those entries Z, again, to be ID normal entries, but in this case, your matrix Z is no longer square. So it's a matrix of size P times N. P times N, okay? And what you're assuming in this case is that P and N grow together to infinity while having a ratio of gamma. What does that mean? It means that you have a sequence, think of it as, N1, P1, and then N2, P2. You have a sequence of tuples, right? Both N and P go to infinity, and the ratio tends to gamma. Gamma is a scalar, right? So for example, if gamma is 1, it means that P and N are tending to infinity, and their ratio is tending to 1, which means they are equal. Now, what we care about in this case is this quantity. So this is the ZZ transpose. You can think of it as a second moment matrix. Why is this a second moment matrix? Because it's basically a sum over ZI transpose, right? From 1 to N. Now, notice that the reason there is a 1 over N here is because this 1 over N is, does anyone know why would you need a 1 over N here? Why is this the correct variance to be using?
Is it so that the magnitude of the rows doesn't diverge to infinity?
Yeah, but even more simply, it's that if N tends to infinity, then this thing converges to an identity, right? Basically, it's my interpretation of the 1 over N is that it's like, here's an alternative thing you could do. Let me put it in red. Imagine if instead we said Zij is distributed normal with 0, 1, and we look at the matrix ZZ transpose 1 over N, which is equal to 1 over, oops, this is an ugly N, sum over I from 1 to N, Zi transpose, right? So basically the 1 over N is making sure that your second moment is in fact the second moment, because in a second moment you need to divide by N, right? Does this make sense? It does. Now, one can ask themselves, what is the distribution of the eigenvalues of ZZ transpose? Again, I emphasize when P and N tend to infinity at a ratio gamma. So here you can see an experiment where, again, what was done was I didn't do this, but another person took the eigenvalues of this matrix and just calculated the histogram of the eigenvalues. And you can see how there is also a green curve on top. This green curve is a prediction. It's a prediction of where should the histogram tend to as the dimensions tend to infinity. And you can see beautiful agreement between the prediction and the histogram, right? Now, this law or this distribution of eigenvalues is called the Marchenko-Pastur eigenvalue distribution. Why is it called the Marchenko-Pastur eigenvalue distribution? Because it was discovered by Marchenko and Pastur. Here you can see the formula for the Marchenko-Pasteur distribution. And what you should notice is that the distribution is, so this is the probability density. What is lambda gamma? So lambda is the lambda here. So you can think of it as the, you know, right? And gamma is just the ratio, the ratio. The ratio is very important. Now, one thing that's important to notice is that this quantity right here is only defined if lambda is in the range. So this is just an indicator function that is constraining the probability density function to be in the range lambda minus and lambda plus. In human words, what does this mean? It means that the probability density function has a finite support, right? And you can actually see that the lambda plus is equal to 1 plus square root of gamma, and lambda minus is equal to 1 minus square root of gamma, right? Now, maybe I should just draw this so it's perfectly clear. Here, this is lambda plus. You can think of lambda plus as just an upper bound almost. It's like where the distribution becomes, the probability density function becomes 0. And here you can see lambda minus, okay? Now, what is the interpretation of finite support for this distribution? What is the interpretation? The interpretation is that as the dimensions tend to infinity, the probability of finding an eigenvalue outside of this support is 0. Is this a satisfactory answer, Amireza? What's the reason so? I think this is part of why this is a beautiful result, because it's, you're not convinced. So this is a highly non-trivial result. If you want to convince yourself, I would highly recommend taking a random matrix theory course and looking at the proofs. But I'm not sure, how can I convince you, Amireza, without showing the proof? I guess you're looking for intuition. Why would the eigenvalues be?
Could you make an argument with the Gershgorin circle theorem that like that would at least give you a bound on the eigenvalues?
Yeah. I guess you could, but it wouldn't really answer why, you could imagine shapes, bizarre shapes like this thing, right?
Yeah.
You can imagine lots of things that are not the case. I think you could probably use Gershgorin to bound somehow yeah, I don't have any intuitive reason. Maybe I'll try to think while I speak and see if I can come up with. I think if you are looking for intuitions for this type of distributions, I would look at the physics literature. There's intuitions there, but I don't want to go there at this point. So let us proceed. So notice that, oh, and I can give you a book if you want. That's a physical perspective on random matrix theory that might be providing some intuitions. So notice that in this distribution, there is a parameter gamma. And in this specific plot, I believe it was set to 1, ratio 1. But one can try and see how does this function depend on gamma. So here you can see when it says gamma, it actually means rho. So here you can see the different curves for the different gamma ratios. So for example, when gamma is, oh, sorry, in the previous plot, it wasn't gamma equal to 1. I think it was something else. So here you can see, for example, this is gamma equal to 0.1. In green, you can see gamma equal to 0.5. In red, you can see gamma equal to 1, and so on, right? Now, one thing that's very nice about this plot is that notice that as gamma tends to 0, what happens with the distribution? Does anyone see it? What's happening with the distribution as gamma tends to 0? More skewed to the left. Yes. Similar support. Converges to delta. That is correct. Mireza is correct. So indeed, as the gamma tends to 0, you would get something that becomes closer and closer to a delta function. I guess it should go to infinity. And this is the most crooked delta function I've seen in my life. Okay, so why is this the case? Why is this the case? Does anyone know? Why would the distribution converge to 1? So let us look at the previous slide and contemplate what would we expect to happen as gamma tends to 0. I have a hint for you. The answer is on the slide. The answer is on the slide. So this is gamma, right? Or I guess this is what gamma tends to. So notice that gamma is the ratio of P over N, right? So you can think of P, if P over N is tending to 0, it means that N is extremely large compared to the dimension P, right? So because of that, it means that we can think of the second moment as just N tending to infinity, right? And if N tends to infinity, we know that this is basically converging to the expectation, which is just an identity. So in simple words, if gamma tends to 0, you're essentially in a case where your dimension of Z is significantly smaller than N. And so it's as if you're calculating this quantity with N tending to infinity, which is as if you're calculating an expectation of ZZ transpose, which converges to an identity. I guess I should start by saying that the eigenvalues of an identity matrix are all equal to 1. Maybe that's the most important thing to say. Did any of these sentences make any sense? Oh, Luke says, instead of explaining anything, just look at the beautiful result by Marchenko and Pasteur and notice that as gamma tends to 0, this becomes basically 1. That is also correct, yes. Is there a critical gamma for gamma below which the matrix is invertible? Yeah, so it's basically gamma equal to 1. Gamma equal to 1? Yeah, I think gamma equal to 1. If a matrix is a square, then you're right on the edge of being invertible, so to speak. If a matrix is, yeah, so 1 is the answer. So I should mention that the way a statistician would look at this is the following. So a statistician would say that ZZ transpose is a second moment matrix. And we know that if we had infinite samples, then our second moment matrix would converge to an identity. And if our sample size is less than infinity, so it's limited, then it means that the dimension of the data, which is P, is comparable to the dimension of N. And if the dimension of P is comparable to the dimension of N, then your second moment matrix no longer converges to the population, it's called, to the population second moment matrix. So there is a population second moment matrix and there is an empirical second moment matrix. The population is an identity. The empirical is what you get if your sample size is not infinitely larger than your dimension. Do any of these words make any sense? Or do you prefer no statistical language? No statistical language it is. So, okay, so it seems like we're out of time. So I think this is a natural place to stop. So thank you very much for joining, and I will answer some questions.
I just have a quick question with the assignment. So when we're trying to multiply two vectors, and I want to take the transpose of one, do I need to turn it into NumPy or something?
No. You just do dot capital T.
Oh, okay, perfect. Thank you.
And more generally, it's at this point, I think almost everything that you have in NumPy or SciPy or AnyPy is in PyTorch. So there should almost never be a reason to convert to NumPy.
Very perfect. Thank you.
I have a question about